So welcome everybody to this meeting of the Western Hemisphere Virtual Symplectic Seminar. We're really happy to have Amanda Hirschi from the University of Cambridge, who's going to tell us about global Kuranishi charts and a product formula.
Thank you very much for the introduction and of course the invitation. So let me share my screen. As you might have guessed from the abstract, this is of course going to be a talk about symplectic Gromov-Witten theory. And it will be somewhat technical, but kind of the slogan of this talk is that we now have a nice and easy way to define Gromov-Witten invariants in arbitrary genus for general closed manifolds. And essentially, all we need is some geometric gadget and then an invariant, which you know since undergrad algebraic topology, to define your virtual fundamental class. So all I'm going to talk about is joint work with Mohan Swaminathan. Now, so let me give you an overview of my talk. I will first give some background, introduce kind of all the words in the title, and state our main theorem, which just says that we have such a global Kuranishi chart for the moduli space of stable pseudoholomorphic maps. In the second part, I will go into more detail and explain or kind of give the construction of our global Kuranishi chart and explain which auxiliary data we have to choose and why we have to choose them. And in the end, I will show you why you might like to have such a global Kuranishi chart, why it makes your life simpler by proving a product formula for symplectic Gromov-Witten invariants. This formula just essentially says if you have a product of symplectic manifolds, you can express its Gromov-Witten invariants in a kind of simple way using the Gromov-Witten invariants of the two factors. Okay, now. So I say this is about symplectic Gromov-Witten theory. So what I'm essentially doing is just counting curves. Or in other words, I want to define an intersection theory on the moduli space of stable maps, or moduli space of some pseudoholomorphic curves. Now for this, our moduli spaces should be compact because in the end we want to get finite counts. Preferably they should be smooth because we know how to do intersection theory on smooth things, less so on singular things. And there's an additional kind of problem here that even if they are smooth, they might not be of the expected dimension. And so we want to actually, that we want to somehow account for that we have this non-regularity of the Cauchy operator. And finally, of course, we want to get symplectic invariants. So our curve counts should be independent of the almost complex structure. We know how to kind of relate different moduli spaces of smooth curves, which are pseudoholomorphic with respect to different almost complex structures. And somehow we want to have a similar thing for whatever thing we build on top of these moduli spaces to get curve counts. So the problem of A has been solved by Kontsevich 30 years ago. He introduced the notion of a stable map, and by Gromov compactness, the moduli space of stable maps representing a given homology class will be compact. So we're good with that. Now the problem is that in order to get A, we will rarely be able to achieve B, for essentially two reasons. One reason is that stable maps might have slightly singular domains. So you need gluing statements. We have a good gluing statement, which just gives you a topological manifold, which is essentially good enough for most intersection theoretic purposes. The bigger problem is that you have to allow for multiply covered curves, which kind of mean that you might not have regular curves for you might have to allow for non-regular curves for any almost complex structure in your manifold. And then you can either restrict to a certain class of manifolds where these things live in a sufficiently high codimension, or you have kind of to do more work to get counts or in intersection theory. And yes, the point of things being of the expected dimension already kind of becomes a problem in the very simple case where you look at constant maps into your symplectic manifold X, because this moduli space here will have kind of a dimension which is too high by g times the dimension of x, again, for reasons of non-regularity. So you need kind of to do more work to do that. And I will explain a model in which you can resolve that. And okay, the last part C is not really such a problem. We know how to deal with this, essentially using the notion of cobordism. Also, which I've not mentioned here, because of isotropy, our modular spaces, even in the best case where they're smooth of the expected dimension, might be orbifold, so they have orbifold singularities, which means that we have to work with rational coefficients. So our curve counts in general will not be integers, but rational numbers. Okay, now to return back to the problem of smoothness, essentially the solution which most virtual frameworks have pursued is to construct a homology class, which essentially behaves like the fundamental class. So it should live in the expected degree, and it should restrict, or it should be kind of the normal fundamental class in the case when your moduli space is cut out transversely. And I say put homology in brackets for the simple reason that this class will usually not live in singular homology, but in something like the dual of check cohomology or in check homology, because these theories have nicer continuity properties. Okay. Now, let me set up notation. So throughout this talk, X will be a closed symplectic manifold, and J will be an omega tame almost complex structure on X, which we kind of now fix as well. A nodal J-holomorphic curve in X is a continuous map from a domain C like this to X. And C you obtain just by gluing kind of, you have a collection of Riemann surface, closed Riemann surfaces, and you just glue them together at double points. So you get these nodal points here. So you have some singularities, but they live in codimension 2 and are kind of quite nice. Now, any such surface admits a normalization, which is simply given by kind of detaching all these closed Riemann surfaces from each other. And we say U is J-holomorphic if its pullback to that normalization is a J-holomorphic map. So essentially we can do differential geometry on C by using the normalization. We can also add mark points to our surface C, as you see here. And we require these mark points to always be in the smooth locus of C, so away from the singular points. And we say that C x1 to xn is of type Gn if C has arithmetic genus G, and you have n mark points. Now, the arithmetic genus, you simply get this by smoothing out these nodes. So in replacing the node in the small neighborhood of this by a kind of small cylinder, so you get just the topological surface, and then you count the genus of that to get the arithmetic genus. By Gromov compactness, we essentially get a compact space as soon as we add J-holomorphic curves of this domain where you have to fix, you essentially have to put an energy bound, but you can also just fix a homology class which your curves have to represent. The problem is that you might have kind of too many curves. So the presence of ghost bubbles essentially means that your modular space might not be housed off. And let me say this in different words. So we say a map is stable if its automorphism group is finite. And yeah, here I mean with automorphisms, just complex automorphisms C, which preserve the mark points and which also preserve U. Now, given some irreducible component Z of C, so just the path component of the normalization, this just means that one of the following conditions has to hold for Z. Either the restriction of U to Z is non-constant, the genus of Z is at least 2, because any Riemann surface of genus at least 2 has finitely many automorphisms, or the genus of Z is equal to 1 and Z has at least 1 nodal or mark point, or finally Z has genus 0 and at least 3 nodal or mark points. In the curve you saw before, this would mean for U to be stable, it would have to be non-constant on both of these spheres because they don't have enough kind of special points to stabilize them. Now, this is also exactly the same condition you need for the kind of notion of stable curve in where you forget about map U, or equivalent, you just take Z to be a point, in which case this first condition never holds, and you have these three conditions, which your curve C with x1 to xn mark as the marked points has to satisfy. Now, the moduli space of stable curves is compact on its own. To get compactness of a moduli space of stable maps through a general symplectic manifold, we need to choose an additional piece of data, as mentioned before, which is just a homology class in degree 2, which I will call beta. And we just take the moduli space of stable maps to X, representing beta, to be the collection of all of these tuples, where we put kind of the obvious conditions of J-holomorphicity, and yeah, type Gn, and stableness, and we quotient this collection by reprimitivizations of the domain, which kind of map mark points to mark points. Are there any questions about this? Okay. Now, maybe let me go back again. So this moduli space is compact by Gromov compactness and it's Hausdorff. However, it will usually not be a manifold and not even an orbifold. And so to get somehow a nice invariant out of this, which lives in the expected degree, you have to kind of do something. You can't just have this moduli space on its own. And kind of the easiest thing to be, like the nicest situation you could hope for is if this moduli space is the CO locus of an orbibundle section. Because then you would actually know what invariant is kind of very natural. Namely, if you have a finite dimensional vector bundle over some manifold and a section was CO locus is compact, or it doesn't even have to be compact, we have kind of a natural invariant, which is the Euler class of this bundle, which we can lift to a essentially cohomology class on the CO locus using Poincare duality. Now, this is essentially the situation a global Kuranishi chart wants to model. So if you're given some space M here, then a global Kuranishi chart for M consists, first of all, of a symmetry group G, which we will assume throughout to be compact, and some manifold phi, which we call T, which we call the thickening, for reasons which will become apparent as soon as I talk about the construction. So we assume that T is a G manifold where G acts almost freely and also locally linearly. And this second condition is kind of a technical assumption, which is always satisfied if T is smooth and G is a smooth group, G acts smoothly. Now, we also have an obstruction bundle, E over T, on which G acts as well, and an equivariant section of E. And finally, we need to connect this, of course, to M. So the additional last piece of data of the global Kuranishi chart, which is usually omitted from the notation, is a homeomorphism from the zero locus of S mod G to M. Yes, for the next definition, so this definition works if M is non-compact, but for the definition of the virtual fundamental class, we need M to be compact, and I will assume this from now on. Now, the virtual dimension of M with respect to this Kuranishi chart is simply given by the dimension of T minus dimension of G minus the rank of the obstruction bundle. And I think you can easily see in the case where the obstruction section intersects the zero section transversely, this here is just the dimension of this orbifold here. So kind of, yeah, it's in some sense a natural notion of extension of dimension. And now the virtual fundamental class of M with respect to a global Kuranishi chart lives in the dual of check cohomology in degree the virtual dimension of M, and it's given by this one line where we use on one part a lift of the Euler class of the obstruction bundle, and then two isomorphisms to kind of pull this back to a map from the check homology of M to just Q. And this again holds because of this technical assumption of local linearity and because we have finite isotropy, and of course, because we also have rational coefficients. Yes, I think it's quite immediate to see that in the case where S intersects the zero section transversely, this just gives you the fundamental class of the orbifold M. In the case where G acts freely, you can of course also use integer coefficients instead of rational coefficients. Yes. So this is kind of like, this is quite a short definition, in particular of the virtual fundamental class, and it requires very little kind of machinery. So we proved that the moduli space of stable maps to X of arbitrary genus and of arbitrary number of marked points admits such a global Kuranishi chart. And
so Amanda, before you get into the theorem, I see that Chris has a question.
Oh, yes, I'm sorry.
I was wondering whether manifold means smooth manifold or topological manifold or something in between in this definition.
In this definition, you just need to be a topological manifold.
But that's why you're adding the words locally linear, I guess,
yes,
when you talk about the G action. Okay.
But you can put any kind of note, like you can ask for a smooth global Kuranishi chart, for example.
Right, except that I assume that would be much harder to construct.
So, I mean, what we do is we get something in between. We get some notion of relative smoothness. And what Abouzaid McLean-Smith do is that they construct a kind of a topological Kuranishi chart, say, and then use smoothing theory to put a smooth structure on the thickening on the obstruction bundle. So
okay,
in some
thanks.
sense, yeah. Yeah, essentially, more or less everything goes through just assuming topological, but like to do the intersection theory is harder. Okay. Yes, so we proved that this moduli space admits a global Kuranishi chart of the expected dimension, simply given by the index of the Cauchy-Riemann operator. Now, this chart is not unique, so the construction requires certain choices of auxiliary data, which these choices are absolutely not canonical. However, the two global charts coming from different sets of choices are actually related by natural equivalence moves, which I will describe later. In particular, the virtual fundamental classes will be exactly the same. And the other kind of uniqueness result we show is that if you're given another almost omega tame almost complex structure, J prime, then we can choose these auxiliary data in A in such a way that the global Kuranishi charts for the moduli space of stable J holomorphic maps and respectively for the moduli space of stable J prime holomorphic maps are coordinate, kind of in the obvious notion of coordinates you would assume between Kuranishi charts. So, as Indy said before, in particular, there exists a well-defined virtual fundamental class, which is independent of the choices you make. Now we can combine this with two natural maps on the moduli space of stable maps, namely an evaluation map to x to the power of n, which simply evaluates a stable map at its marked points, and a so-called stabilization map to the moduli space of stable curves. Of course, the second map only exists if we're in a stable range. So if 2g minus 2 plus n is strictly positive. And in this case, the map simply forgets the map, the stabilization map simply forgets the map u to x, just remembers the domain and collapses components which become unstable as soon as you kind of no longer have the condition that u is non-constant on your irreducible component. Now, kind of given these two pieces, we can define Gromov-Witten classes of X, where we also have kind of to put in this omega and Gn and beta to put forward of the virtual fundamental class under the product of the evaluation and the stabilization map. And this will then kind of define a class, homology class on x to the power of n across the moduli space of stable curves which is independent by the second part, or like the last part of our theorem, of the choice of almost complex structure. Okay. Now, let me say a few remarks about this. So, kind of describing the moduli space of stable maps as the zero locus of some orbibundle section was done before. It's kind of commonly, I think, commonly known under the name of finite dimensional reduction. However, previously we had such descriptions only locally, which meant that you kind of had many different thickenings, which might have different dimensions and many different obstruction bundles, and you somehow had to extract a global invariant out of these many local models. And this meant that you had to use kind of quite complicated and technical machinery to construct your virtual fundamental class. Now, Abouzaid, McLean, and Smith were the first to construct such global Kuranishi chart for moduli spaces of stable maps. They constructed them only in genus 0, however. And they not only used this to kind of define or get a kind of neat definition of a rational virtual fundamental class, they also used this to define a Marva K-theory valued virtual fundamental class, which means that you essentially can do or can define Gromov-Witten classes or class. It's not really classes anymore, but essentially you can look at Gromov-Witten invariants in generalized cohomology theories. So kind of also related is work by Xiaoyun Bai and Guangbok Su, who kind of use global Kuranishi charts to construct integer valued Gromov-Witten type invariants in any genus. So they did this so far only in genus 0, but as far as I understand from the paper, you can use their machinery with our global Kuranishi chart to obtain them in any genus. Okay, are there any questions about this? Now, let me say a few further applications kind of to motivate my second part a bit more. Mohan and I, we prove a virtual localization formula, which is kind of analogous to, like it's an Atiyah-Bott localization formula, and very similar to the localization formula you have in algebraic Gromov-Witten theory. And it just means that if you're given some global Kuranishi chart with some compatible torus action, which is sufficiently nice, then you kind of can compute the virtual fundamental class of the space M using just the fixed point locus. So you can get a global Kuranishi chart for the fixed point locus of your space M, and yeah, the formula describes how these two virtual fundamental classes are related. We're in the process currently of proving the Kontsevich-Manin axioms for these Gromov-Witten classes I defined before, which actually uses a very similar approach to the one I will describe later when I prove the product formula. Since global Kuranishi charts are quite similar to this intrinsic normal cone, which is used to define algebraic invariants, one might also hope that global Kuranishi charts help or will be useful in a comparison of algebraic and symplectic Gromov-Witten invariants. And of course, you might want to construct global Kuranishi charts for other moduli spaces of pseudoholomorphic curves or of other geometric objects, and they might be useful kind of in many other fields. Okay, are there any more questions before I go on to the construction? Now, for autoconstruction, we will assume, or I will assume, that we have no marked points. The case with more marked points essentially follows formally from the one I will present here, and it will simplify notation. So we first fix a few auxiliary data, namely we'll fix a J-linear connection nabla on the tangent bundle of X, which will help us just get holomorphic structures on certain vector bundles over Riemann surfaces. And more importantly, we fix a so-called polarization or X1 on X, which is a Hermitian line bundle whose curvature is of a kind of specific form. Namely, we require the curvature to be equal to 2 pi I omega, where omega is the symplectic form on X which also tames J. And you should think of as omega as some kind of rational approximation of the symplectic form we started with, which is then multiplied by a sufficiently high integer. Now, given a smooth stable map U from C to X, we define the line bundle LU to be the tensor product of the dualizing sheaf of C with the pullback of OX1 tensor 3 times with itself by U. Now, if U is J-holomorphic, we see that by the stable condition, this line bundle actually has positive degree on each irreducible component of C. And this means that we can find some sufficiently high integer P such that this line bundle here, so the tensor power of LU, P tensoring LU T times of itself, will be very ample. Now, since this P essentially depends only on the topological type of C, and we have only finitely many of those appearing in the moduli space of stable maps, we can find actually uniform P such that this line bundle is very ample, and also such that the H1 of this line bundle vanishes. Now, the very ampleness condition essentially just means that we obtain a framing, I will call it framing, but it's essentially just an embedding iota of C into projective space, with which is kind of not quite uniquely characterized, but almost uniquely characterized by the fact that the pullback of the O1 line bundle on Pn to C will be isomorphic as a holomorphic line bundle to this LUP, LU tensor P times of itself. Since the H1 of this line bundle vanishes, this in particular shows you that these embeddings are unobstructed. And since the embeddings, they have, of course, no isotropy. Okay, so this framing is essential. You should think of it as kind of like a graph trick, I guess. In other words, it gives you kind of full view of the domain C. So if you want to add, like in general, if we want to add perturbations to a moduli space of stable maps to achieve transversality of the Cauchy-Riemann operator. And the problem is that we can't really access the domain C just like that. And so we need some kind of additional piece of data to access that domain. And what, for example, Pardon does in his implicit atlas construction for the moduli space of stable maps is that he adds marked points to the domain, which make it stable. And so you get an embedding into the universal curve over the moduli space of stable curves. However, the problem with this approach is that you need to choose these added marked points in a kind of coherent or continuous way. And the way you do this is the way Pardon does it is that he uses hypersurfaces inside the target manifold X. And you kind of look at the open locus of J-holomorphic curves which intersect this hypersurface transversely, and where the preimage of the intersection stabilizes the curve. Now you see that kind of these conditions actually mean that you will not be able to have a global chart, a global Kuranishi chart, because these assumptions are rarely achieved globally. And so kind of it was a nice idea by Mark McLean to use instead framings to get full access to these domains. Yeah. Are there any? Okay.
Yeah, can I ask a question, Amanda?
Yes.
In the definition of LU, where does the power 3 come from?
The point is just that, so this has domain, this has essentially, if C is smooth, this will have, how to say this? Okay. It's essentially just tailored to make this positive on every component, on every irreducible component, to have it irreducible. Yeah, how to say this? So the degree of this line bundle is always positive, essentially because by this condition. And if you wish to stick to some component, you see that in some sense, you would need to either add at least 3 marked points. And so instead of adding 3 marked points, you add somehow this line bundle. Does that make sense? Not quite. Okay.
Yeah, more or less. Thanks.
So, okay, like Okay, yeah, this line bundle, this line bundle has positive degree on any component of C which is stable on its own. And so you're only left with actually just the case where the component Z has genus 0, in which it might be unstable. But if it's unstable, then you will be non-constant on that component. So this line bundle will have positive degree, and you just want it to have at least degree 3, because otherwise this is degree -2.
I understand.
Okay.
Thank you.
Sorry, that was a bit of scrambled explanation. So our thickening will essentially consist of smooth stable maps of our given type, represent our given homology class, and some additional pieces of data. So we also given a framing of C into kind of a uniform projective space, Pn, which are supposed to be of degree n+g. And this is actually the degree of our line bundle LU tensor P times with itself. Now, in genus 0, kind of the pullback of the O1 line bundle under Pn under iota is kind of, it's uniquely determined by its degree. In higher genus, it's not, because you have the whole pic 0 of C. And we use an additional piece of data, alpha, in H1 COC to kind of control how far iota is away from and pulling back this O1 line bundle to LU tensor P times with itself. So you should see this equation as inside pic C, or like some component of the Picard group of C, which is just a torus of dimension 2G. And finally, we have our perturbation term eta, which lives kind of in this big obstruction space here, where the kind of the important bit is that we have this very positive line bundle here and here, and this will be used to achieve transversality. And K is an additional piece of data which we have to, like additional auxiliary data which we have to choose, which I will not do now. So you can do this construction so far for any K. And we use this perturbed Cauchy-Riemann equation, where these brackets just mean that we pair the part of eta coming from this line bundle with the part coming from this trivial line bundle here, using the Hermitian inner structure on OK, Hermitian metric on OK. Okay, now, so we add kind of some additional stuff to our moduli space of stable maps. So we kind of thicken it up. Now we have to take this away again. And the obstruction bundle is essentially tailored to do that. So the first part is the Lie algebra of PU n+1. The second part is this space where alpha lives in. And lastly, we have our perturbation space. The first part I will explain in a bit. The other two parts should be clear. So both E, the obstruction bundle, and T admit a natural action by PU n+1. Now this PU n+1 action extends to the PGL n+1 action over the locus where the perturbation term eta vanishes. And what does this action do? So in both cases, it acts on the framing iota, simply by post-composition using the obvious action on Pn. And if we are over the locus where eta doesn't vanish, we actually only get a kind of well-defined action by PU n+1. But of course, over the locus where eta vanishes, we can extend that. And this is a bit of a problem because we have, in some sense, we have a PGL n+1 worth of embeddings of a curve C into projective space, which pull our line bundle back to a line bundle which is isomorphic as a holomorphic line bundle to LU tensor P times of itself. But in the end, we want to quotient by compact group action. So we somehow have to select a slice inside a PGL n+1 worth of embeddings. And this is the reason we have this first term here. And this is also the reason we have this kind of ugly looking term in our obstruction section here. So this obstruction section simply maps a tuple like this to, of course, in the second component, alpha and eta. And in the first component, we have a map on one which is composed of the polar decomposition for PG on the kind of level of PGL and PUN+1, and another auxiliary datum which we have to choose respectively construct, which is simply a PUN+1 equivariant map from the thickening T to this quotient, which is PGL and +1 equivariant over the locus where eta vanishes. Now, kind of to summarize all of this and see that we actually really get a global Kuranishi chart for a modular space of stable maps, we know that if the obstruction section vanishes, we on one hand have that our curve is actually J-holomorphic because the perturbed Cauchy-Riemann equation is just the normal Cauchy-Riemann equation now, and that our line bundle iota actually pulls back the O1 line bundle to LU tensor P to a line bundle isomorphic to LU tensor P times of itself. And as said before, we have a PGL n +1 worth of such line bundle of such embeddings. And now we restrict this to a PU n +1 kind of worth of such embeddings using kind of this slice function here. And this shows that the zero locus of S quotient by PUN +1 actually gives us back the moduli space of stable maps if we simply forget the embedding. Okay. So I still promised you that I would tell you kind of how to choose K. I mean, I will not really do this explicitly, but the point is for each curve, if we go back, if you have some stable map with some embedding, then we can choose this K sufficiently large that we can use such perturbations living in this space here to kill off everything living in the co-kernel of the linearization of the Cauchy-Riemann section at U. Now, since this locus here is compact and kind of we have every J-holomorphic curve admits an embedding coming from this line bundle at U such that it lives in here, we can choose this K in a uniform way so that this equation is cut on transversely near the zero locus. Where I say, yeah, where we use that regularity is an open condition to extend it actually to a zero locus. So we can somehow, yeah, we can just find such a K to get an unobstructed moduli space. And to see that this is actually kind of a topological manifold, we use a shearing trick to show that this locus T-reg is actually a covering over a moduli space of regular embedded stable maps into a different symplectic manifold, which is essentially a vector bundle over X cross Pn. Now, you of course have a map from a thickening to the moduli space of stable maps to projective space, which simply forgets everything but the framing. And since the framing is a regular embedded curve holomorphic map into projective space, it will actually have image in a nice subset of this moduli space, of the moduli space of stable maps to projective space, which is in particular has no isotropy and which is of the expected dimension. And with respect to this map, the locus T-reg naturally has a relative smooth structure. So the map itself, you can show that it's a topological submersion, but it might not be smooth in any way. But its fibers are smooth. So we have like a vertical direction, which has smoothness, in the horizontal direction, which don't have smoothness. But this is actually enough for most purposes. Okay, so to summarize all of this, the global Kuranishi chart we use in the end has covering group PUN +1. The thickening is given by this T-reg for some choice of sufficiently high K. And the obstruction bundle and the obstruction section are given the same way as I defined before, simply restricted to this regular locus. Okay. So let me quickly say in what are these natural equivalence moves between different global Kuranishi charts. The first one is called germ equivalence, and it simply says, so we start with some global Kuranishi chart, as you see here. And if you have some G-invariant open neighborhood of the zero locus, then you can replace the thickening T with that neighborhood U and just restrict the obstruction bundle and obstruction section to U. Another equivalence notion relation is so-called stabilization, and it says that if W is a G vector bundle over the thickening, then you can replace the thickening by W, which means in some sense you just add more information to the thickening. Now, to get kind of the same space back, you also have to add this information to the obstruction bundle. So the obstruction bundle will simply be the pullback of your original obstruction bundle summed with the pullback of W itself. And the obstruction section will be the pullback of the original obstruction section and the diagonal section of W. So it's all the information you add to the thickening, you take away again using an enlarged obstruction section. You can also enlarge the covering group. So if we have a principal G prime bundle P over T, which admits a compatible G action, then we can replace our original Kuranishi chart, global Kuranishi chart, with a Kuranishi chart whose covering group is G cross G prime, and the thickening is P. And you see that in this case, we in some sense take the additional information added to the thickening away again using the group action. So we don't have to change the obstruction bundle and the obstruction section. We can just pull them back from T. It's not hard to show that the virtual fundamental class stays the same under these equivalence notions. Now, for the last kind of relation between global Kuranishi charts you can have, it's the relation of cobordism. So if you have two global Kuranishi charts which have the same covering group, we say they are cobordant if there exists a global Kuranishi chart with boundary and which has the same covering group, and we simply require the thickening to have boundary which is equal to the disjoint union of T0 and T1, the thickenings we started with. And such that the obstruction bundle restricts to the disjoint union of the obstruction bundles E0 and E1 over the boundary, and such that also the obstruction section restricts. We don't put assumptions kind of on the zero locus of our Kuranishi section S, but yeah, in general, it will also, of course, not be like something like 0, 1 across the zero locus of your sections here. The way you achieve, for example, this relation, if you're given two different almost complex structures on X, is that you choose a path between them. And kind of the only point you have to notice is that these auxiliary data I chose, you can choose them in a uniform way to explicitly kind of construct a cobordism of charts of perturbed, say this, of thickenings of your moduli space. Any questions about this? Okay. So let me go to my application and prove, kind of state and prove the product formula. So this is formula which was conjectured by Kontsevich and Manin in the paper where they kind of defined the Gromov-Witten axioms. And it says, it's just a very neat formula of, or essentially says the Gromov-Witten classes of a product of symplectic manifolds, say X0 and X1, are what you would expect them to be. So we now restrict to the case where X is such a product and where our almost complex structure J is the product of omega I tame almost complex structures Ji. We fix homology classes beta 0 and beta 1 of degree 2, and we let this moduli space here on the left be the disjoint union over all moduli spaces of stable maps to X representing beta, such that the push forward of beta to X0 and X1 is beta 0 and beta 1 respectively. Now these projection maps also give projection maps between this moduli space on the left to, on one hand, the moduli space of stable maps to X0 and the moduli space of stable maps to X1 And we combine them to get this product map. Now, because of the stability condition, this map doesn't just simply project a curve U like this to the kind of projections of U to each factor using the same domain, but you have to change the domain to kind of retain stability. So in this case, for example, we see that the projection of U is constant on this sphere here. So if this map has to collapse that sphere to get a well-defined stable map, and kind of vice versa for the other sphere down here. But you're still continuous like that. Now, kind of an important thing to notice that in some sense, you can think of these contractions of components which become unstable after forgetting one factor as partial stabilizations. And this also shows you that if you get now the map U 0 completely and stabilize the remaining domain, then you get the same thing as if you would forget the map U and stabilize the domain. My example is not quite great because this curve is not stable if you forget the map U. But in general, you see that the stabilization of the domain of U0 and the stabilization of the domain of U1 are the same. And actually the image of this product map is exactly the fiber product of these two moduli spaces over the moduli space of stable curves. But it's in general not injective. Okay. So in the case where you are in a stable range, so 2g minus 2 plus n is strictly positive, and we also have to exclude the two cases where gn is equal to 1, 1 or to 0 is to 0. Then we have the following relation between the Gromov-Witten classes of X and those of its factors. So the sum over all beta such that it projects to beta 0 and beta 1 respectively is equal to the intersection of the Gromov-Witten classes of X0 and X1 with respect to beta 0 and beta 1 capped with the pullback of the Poincare dual of the moduli space of stable curves. In particular, if we restrict to the case where g is equal to 0 and n is equal to 3, this moduli space here will just be a point. So we just obtain, so we can forget about this term and just obtain these two classes, the tensor product of these two classes. This just means that the small quantum cohomology ring of X is actually isomorphic via the Kunev isomorphism to the tensor product of the quantum cohomology of X0 and with the quantum cohomology of X1 over the universal Novikov ring. So do you want me to do 50 minutes or can I go a bit over time?
Something relatively close to 50 minutes, but you can go a few minutes over if you'd like.
It will not be long. So I've mentioned before that if you fix a global Kuranishi chart as I've constructed before for you, it comes equipped with a topological submersion to this nice moduli space of embedded regular maps into projective space. So now we have two of these submersions, one for X0 and one for X1. And we can actually use this together with a different map to build a new global Kuranishi chart for our moduli space here into X, this disjoint union of moduli spaces. Namely, we of course also have a product map for the product Pn0 cross Pn1 to this to the product of moduli spaces of stable maps to on one hand Pn0 and Pn1. And then we can just take the pre-image of this open subset in the full moduli space of stable maps to get a nice smooth unobstructed subset inside the moduli space of stable maps to the product, which also has no isotropy. So we have the restriction of this map will be a smooth map, and it will also be proper. And even more importantly, it's a birational equivalence onto the fiber product of these two moduli spaces over the moduli space of stable curves, considered as an orbifold. Now, we can, in some sense, pull back the global chart T0 cross T1, we're thickening T0 cross T1, living over this product using this map. So we construct a new global Kuranishi chart for our model space, which we had before on the left-hand side. Both thickening is given exactly by the fiber product of these two things over the product of nice moduli spaces of stable maps to projective space. And we pull back all of our data from the global Kuranishi chart we have on the right. So we pull back the obstruction bundles and the obstruction sections. Now you can show, similar as you show uniqueness, that this global Kuranishi chart is equivalent to the disjoint union of original global Kuranishi charts we constructed for the moduli spaces. So far, kind of the geometry works out nicely. Now we have to exclude these two cases of 1, 1 and 2, 0, essentially just for technical algebraic reasons, because in these two cases, the moduli space of stable curves is an ineffective orbifold. So kind of you don't really count restrict to nice open subsets, which have no isotropy, and kind of do your arguments using just standard intersection theory. You have to kind of be a bit more careful. But if you don't look at these two cases, you get the following relation for the push forward of the fundamental class of our moduli space of nice maps into the product of projective spaces, which just is given by the pullback by capping the fundamental class of M using the pullback of the Poincare rule of the diagonal of MGM bar. So we believe this is also true in general, but it's just a bit harder to show. Now, using these topological submersions, which we have kind of naturally from our construction, this relation actually leads to kind of the equivalent relation between the fundamental classes of the thickenings T tilde and T0 cross T1. And then you can use this to show the following formula or relation between the virtual fundamental classes. And as soon as you push this forward, you get the product formula I showed you before. And that's all I wanted to say. I thank you for your attention.
Let's give Amanda a hand. Questions for Amanda?
Can I ask a question? Oh,
Sure.
Yes, go ahead.
So I'm wondering if we have a similar formula for like fiber bundles over some symplectic manifold.
Yeah, I'm currently proving. I'm working on that. So you can essentially take the fiber if you have closed symplectic manifolds with submersions to another closed symplectic manifold. You can do the same thing, but it's a bit harder because you can't use the given global Kuranishi chart because you don't, if you have the construction we gave before, if you let me kind of go back, is quite non-functorial in a sense. Like you might have different framings into different projective spaces, and there's no clear way there's no clear reason why you should just have a map between different global Kuranishi charts for different manifolds, if you know what I mean.
Yeah.
Okay.
Thank you.
Welcome.
So I wanted to ask a question. So my understanding is that in the usual treatments of non-global Kuranishi atlases, you first cover the uncompactified part of M by Kuranishi charts, and then you build sort of boundary charts and use some gluing theory to show that everything forms a Kuranishi atlas.
Okay.
And I'm wondering, that gluing analysis, what does that sort of transmute into in this sort of treatment?
We kind of push all of that. We just use Pardon's gluing statement. So we say our regular locus is a covering over moduli space of regular embedded stable maps. And he shows that in this case, you're a manifold. We just we kind of just steal his gluing statements, and we don't do any work on that.
I see. So everything goes into the construction of the thickening.
Yes.
Got it. Thank you.
Yeah. Like it's just really that, like the two important kind of ideas are that we this framing, and that you can choose this case sufficiently large, such that this equation is cut out transversely.
Yeah, I see.
Yeah.
Okay. Any more questions for Amanda?
Excuse me. I've got two related questions. First, suppose you're in the nicest possible situation where for some J, your compactified moduli space is already transversely cut out. Then I guess there's an obvious definition of a global Kuranishi chart in which the obstruction bundle is trivial. And it must surely be true that one is cobordant to the thing that you construct, but how obvious is that?
I would actually rather say that should be equivalent, not cobordant.
Okay.
Because you can just show, if you say, in some sense, you can just look at the last part of your section and you say, you know, like the last factor of your section S, in some sense, that's already cut out transversely. So you can just forget about the obstruction term.
So you're saying it's obvious if you look at it the right way. Yes.
Yeah, maybe. Like another thing to notice is that in some sense, this alpha, like this alpha, like the alpha part is also cut out transversely.
Mm-hmm. So my related question is, if you're in a semi-positive symplectic manifold, so you can get transversality for the uncompactified moduli space, and you can prove that the singular strata are somehow irrelevant for dimensional reasons, but still the compactified moduli space is not so nice. Then it's not obvious to me how to define any global Kuranishi chart out of that. But is it clear that the invariant that you define is then equivalent to what you get from the Macduff-Solomon book or whatever else people understood in 1994?
No, it's not. I don't know how you would show that. I mean, I also don't know if it's been example shown for Pardon's invariants, whether they're actually equivalent, as far as I know, to the Macduff-Solomon invariants.
Does anyone else here happen to know that? I'd love to know.
Same.
So Roman, sorry, I just noticed that you've had your hand up the whole time. Why don't you go ahead?
Yeah, so in your text, you're saying that there is another approach being developed by Abouzaid and McLean of these global Kuranishi charts, and maybe you could tell what's the difference?
Yes, I should have said that they have an independent construction. So the main difference, I've not seen their paper, but the main difference, as far as I can deduce from talks, is that they don't use kind of this alpha term to constrain their framings. So they essentially use two framings and then somehow relate them with each other. Yeah, but actually, like, I think the last thing they showed was not quite correct, but I don't know what the actual one is at the moment. So in genus 0, our chart is equivalent to the one they define in their paper, in the first paper. And I think all of us expect that the construction they come up, like they have, is equivalent to our construction.
Okay, any last question for Amanda? Okay, let's thank Amanda one more time.